In everyday life, we subconsciously collect information about the people and environment. Who's around? What are they doing? What can they see? We call this informal awareness. And we use informal awareness to mediate our interactions with others. For instance, we know when others come and leave, and we can see what they're doing. And we use informal awareness to help us to know when we can engage in interaction with others. Head-mounted displays encourage rich immersion into virtual worlds, but they also introduce a boundary between the physical world and the virtual one. We call this the HMD boundary. HMD users cannot see people in their physical environment, so we need to help them understand who's around and what they're doing. We explore how to make the HMD boundary permeable without unduly disrupting the immersion of the headset user. In this research, we explore 3 visualization techniques that present informal awareness information to the headset user about bystanders. This informal awareness information about bystanders is comprised of their location in the room, their head orientation, or what they're looking at, and their bearing, or where they're moving. These techniques consider variations on how abstract the presentation is and where the presentation of the information is for the headset user. In our work, we evaluate them to compare how good they are at providing the headset user with the awareness of bystanders without disrupting the immersive experience. To illustrate how the visualization techniques work, let's take a look at a common VR scenario. Here, the headset user is represented by the red arrow. The direction points to the way in which they are facing. Blue arrows are nearby real-world bystanders in the environment that may be walking around or talking to others in the environment. With the avatar view, bystanders are represented by avatars that show where they are moving and looking. Here on the right, we can see what the headset user sees. The avatars are concrete in their presentation, but their position in the virtual environment maps one-to-one to the bystander's location in the physical space, along with the avatar's nose, which points to the bystander's head bearing. While this approach provides a lot of information that is easy to consume, it may be disruptive to the headset user's experience. Another problem is that it's hard to understand what bystanders are doing because headset users have a narrow field of view. With radar view, we show a mini-map to the top left of the headset user's view that shows where the bystanders are relative to the headset user. This is always centered around the headset user's perspective, so as she turns, so too does the world in the minimap. In contrast to the avatar view, the headset user can see the bystanders all the time in the minimap so long as they are around. With the Presence++ widget, the design is fully symbolic. Here, when icons appear on the top left, these represent bystanders that are in the physical space. When a bystander faces the headset user, as one does right now, eyes appear on the icon. This tells the headset user that a bystander is looking at her. When a bystander approaches the user, the icon grows as the bystander enters the play area. When bystanders are not looking towards the headset user, the eyes disappear. We show up to 3 icons, one for the 3 closest bystanders in the room. We conducted a lab study to understand whether our designs could sufficiently balance awareness with immersion. We designed 3 immersive experiences that vary the amount of interactive engagement required by the user: a first-person shooter game, a drawing activity, and a 360 movie experience. During the study, we asked participants to engage with the content and, as a secondary task, to monitor bystanders in the room and to signal if they thought a bystander wanted to speak with them. We designed multiple scenarios involving 0 to 4 bystanders, where in some cases the bystanders would want to interact, and in other cases where they did not. Based on our study of 12 participants, we found that the avatar view was good at helping people to understand when others wanted to interact with them, but that the Presence++ widget was the best in reducing the disruption to the VR experience. Based on our findings, we discuss how future techniques can be designed to mitigate the reduction of immersion for the headset user while providing them with awareness. These can be found in the paper.